Welcome back everyone. In this lecture, we will define the universal enveloping algebra and see some of its properties. So, this notion of universal enveloping algebra, it is very important for the representation theory of the Lie algebras. So, let us actually start defining and then I will give you motivation why these are important. So, let us start with the Lie algebra G. So, this is a Lie algebra. Again, it does not need to be finite dimensional, but if you are convenient, you can just assume to be finite dimensional. So, again we will take the ground field to be complex numbers. So, recall, so Lie algebra to begin with, it is a vector space. So, in particularly we can talk about tensor algebra of this G. So, let us denote it by Tg. So, this is by definition. So, this is the direct sum of all the k tensors. So, where k ranging from 0 to infinity. So, recall that T0 of G is nothing but the one dimensional space C, and then T1 of G is just G. So, the kth tensors are nothing but you take all possible span of k tensors, in particularly this is the as a vector space is the tensor product of all this G k times. So, now we have this natural product on this space, and that makes it actually this Tg associative algebra. Okay. So, this Tg, this is associative C algebra. Indeed, if you think about it, it is generated by G. So, this is generated by G. What is the meaning of that? If I take T1G, so from this one can obtain all possible TKG. Okay. So, this is exactly the G. So, this actually generates Tg as C algebra. Okay. That is more or less clear from the definition. So, now let us recall the universal property of this tensor algebra. So, like I said, it is indeed free associative algebra generated by G. So, there are no relations that we impose on the basis of the G. So, that means if we take for example any map, okay, from G to some capital A, where capital A is C associative algebra with, let us say, unit 1 with unity 1. So, then given any C linear map, we can always extend that C linear map to Tg. Okay. There is unique extension that we have. So, note that G is isomorphic to T1G. So, there is a natural inclusion, let us call it I. So, this is the inclusion that we have from G to Tg, and that is indeed a C linear map. So, this is just a C linear map. So, now given a C linear map from G to A, we can always extend that map to Tg to A as a C algebra map. Okay. So, this is the universal property. So, there exists extension such that this diagram commutes. So, that means given theta, there exists theta tilde. So, there theta tilde is the extension of theta. So, what is the meaning of that? So, that means theta tilde when you restrict. So, when you look at this composition, theta tilde composed with this I, then you get back theta. So, that is the meaning of this theta tilde being the extension or this diagram being commutative. So, now this is always actually a case for the tensor algebra. So, and the tensor algebra can be defined using this universal property. Okay. So, maybe I will leave it as exercise to prove this. So, what is the exercise? Given theta, from G to A C linear map, there exists unique theta tilde which is from TG to A, which is a C algebra map. So, that means it is a map from map between associative algebras such that, so when you compose these maps you get back theta. Okay. So, this can be proved very easily because Tg is generated by G, that is what we are going to use. Indeed, if you think about it, theta tilde on any tensors, let us call it x1 tensor etc. xk, it will be defined as the product theta of x1 etc. theta of xk. So, that is the only way one can define because G generates Tg. So, now if you take this as definition and then you need to verify that this is well defined. Once you verify it is well defined, it is clear that it is a C linear map, and this map indeed is a unique extension of theta. So, now we are going to actually define what is the universal enveloping algebra. But before that, let us try to understand what is enveloping algebra means. Okay. We are, let us say, in a situation that G being finite dimensional algebra, we can also assume that G just being linear Lie algebra. So, that means G sits inside GL of V, and indeed any finite dimensional Lie algebra over complex numbers can be embedded inside GL of V for some V, that is called Ado's theorem. But if you are in this situation, then we can actually have a very nice associative algebra that can be defined for this G. Okay. So, take this kind of scenario where G is sitting inside GL of V. So, now if you think about it, GL of V is nothing but set of all linear maps from C to C, endomorphism on V, and this is indeed associative algebra. So, this also has this associative C algebra structure. So, if I take G and then if I consider it as element inside subset inside this endomorphism of V, so we can talk about the associative subalgebra generated by G. So, this is the associative subalgebra generated by G inside this endomorphism of V. So, now what is the use of this associative subalgebra that actually generated by G? So, if you think about it, if you have some representation, okay, that is actually so where G acts on that. So, let us say G acts on one can even take this V itself, let us say, because G sits inside GL of V, G naturally acts on capital V. So, now if you think about it, okay, so then the action of this G can definitely extended to the action of this subalgebra, associative subalgebra generated by G. So, this induces action on, okay, let us induces action on capital. Okay. So, now we are actually started with the representation of the Lie algebra, and then we ended up actually defining a representation of associative algebra. Now, one can actually use this dictionary to actually say something about this representation. For example, if we have some information about this associative algebra, how it acts, so then using that information one can get some information about how this Lie algebra acts on V. Okay. And if you think about it, this is in some sense associative algebra that is just containing G, which is sitting inside GL of V, which is generated by G. Okay. It is the smallest associative algebra that contains G. Okay. So, some information about the Lie algebra definitely can be translated to some information about this associative algebra and vice versa. So, that is why at least about this particular representation we can actually always if we know some information about this particular representation capital V of this associative algebra generated by G, then we get the same information about that representation as representation of G. So, this correspondence in some sense very helpful. For example, if V is irreducible as representation of this associative algebra generated by G, then it must be irreducible as G module, okay, that is easy to see. And similarly, the other concepts also one can actually try to see what happens. But there is a drawback in this construction. So, given G, only if we know that it is embedded inside GL of V, then we have this enveloping algebra. Okay. So, I do not want to actually kind of give very precise definition of enveloping algebra, which will not, we will not need it here, but you can easily see that the enveloping algebra is defined something like this, which is the subalgebra generated by G. So, then it motivates us to ask this natural question whether one can do universal construction that actually takes care of all representations. Okay. So, given G, okay, can we define some universal associative algebra, of course, in some sense generated by G, again let us put it in the quote, such that what we want, representations of G corresponds to representations of that associative algebra. Representations of G corresponds to representations of that associative algebra. Okay. So, this is the goal. So, indeed the universal enveloping algebra gives you answer for that. So, let us actually just define what it is. So, then it becomes actually very easy to deal with it. Okay. So, what is the universal enveloping algebra? So, if you think about it, we are interested in actually taking associative algebra generated by G. Okay. So, the TG is also such algebra. Okay. This is also associative C algebra generated by G. But the thing is, this only actually sees the linear structure on G, that is a vector space structure. Okay. So, TG sees only the vector space structure of G. So, we need some associative algebra which is universally constructed, so that it also sees the Lie algebra structure. Okay. So, that means whenever you take, okay, suppose if you think G as, okay, subset of whatever, let us call it UG. So, this is the universal enveloping algebra that we denoted by UG. Okay. So, if it is G is viewed as subset of UG, then if I take x and y inside G and then look at the same elements inside UG, then I can make this product x y y x, whatever that is inside UG I will be able to make. But then if they are elements of G, then this xy minus yx naturally they corresponds to the bracket xy, okay, inside the associative algebra UG. But there is a bracket that is already defined on G. So, we demand that this has to be same as that one defines inside G, okay. Otherwise there is no compatibility condition. So, in some sense this is what motivates us to define the universal enveloping algebra as follows. So, let us actually just define. So, we can just take, let us call it I star, okay. So, this is the two sided ideal generated by x tensor y minus y tensor x minus the bracket xy, where xy comes from G, okay. So, already there is a product in TG. So, that is xy, x tensor y, and then we can talk about the difference x tensor y minus y tensor x. The problem is that may not be equal to the bracket xy, because this is like a degree 2 element and this is degree 1 element, because this is coming from G, okay. But in the universal enveloping algebra, in some sense we want that compatibility, we want them to be equal. So, then just go modulo this two sided ideal generated by this, then you get the universal enveloping algebra. Then UG is defined to be TG modulo this I star, okay. Now, once we actually define this, then you can easily see that the relations that we have defined, they are not graded relations. So, these relations or the ideal generated by whatever this generator, they are not graded. So, because they are not graded, so the UG is not a graded algebra, okay, that is easy to see. So, that implies this is not graded algebra, but there is this grading on TG. So, what that grading will do for UG? So, if you just take the image of that, that is going to give us actually what you call this filtration on UG. So, one can prove that this is indeed filtered algebra. So, this is filtered algebra. So, how one can actually get the filtration? So, you can take this summation T r of G, where r ranging from 0 to k, and then if you take, so let us call the quotient map as pi. So, pi is the map from TG to UG. So, this is a surjective map, and if you take this map and then look at the pi of this filtered component inside your TG, because TG is graded. So, that implies these sums will form a filtration for TG. Then if you call this as UKG, then this will give you the filtration. So, what is the meaning of that? That means U0 of G is contained in U1 of G and so on, and UK of G is contained in UK plus 1 of G. And not only that, this is called filtration if whenever you take UK of G times UK dash of G, that should lie inside UK k plus U power k plus k dash of G. Okay. So, that is why this is a filtration. This is a filtration of UG. So, UG becomes filtered algebra. So, there is a general construction. Once you have a filtered algebra, you can talk about associated graded algebra. Okay. Indeed, the Poincare-Birkhoff theorem talks about that graded algebra. One can prove that graded algebra is nothing but the symmetric algebra of G. So, we will actually not write the PBW theorem in that form, but that will become a corollary. Maybe I will actually state it at the end. But now, let us actually look at this the universal Olympic algebra more closely. So, we have defined the universal Olympic algebra. So, now there is this natural question, okay, whether it has any universal property, and of course, there is some universal property. So, let me just state it here, the universal property of this UG. So, what it is? So, if you think about it, it is a very simple thing to modify. So, we can take the universal property of TG and then just simply modify. So, you take capital A, be again associative, C algebra with unit 1. Okay. Now, denote the bracket A to be the associated Lie algebra. Okay. Maybe Lie algebra of capital A. So, how the Lie bracket is defined? It is given by the commutative bracket. With the Lie bracket, the bracket AB is being AB minus BA for all AB in capital A. So, this is the data is given. Okay. So, now, if you start with the Lie homomorphism, because we need to actually take that Lie algebra structure. If you have a Lie algebra homomorphism from G to the bracket A, which is as a set A. So, this is let us say theta, which is a Lie algebra homomorphism or the map. So, then there is a natural map iota from G to UG. So, what is iota? The iota is the inclusion composition with the quotient. Okay. So, you have a map from G to TG, which is the inclusion I, then TG to UG, you have the quotient map pi. So, if you compose them, then that map you call it iota. Okay. And it is clear that this iota is just a it's actually a linear map to begin with, but the way we defined UG, you can easily see that this iota is indeed Lie algebra homomorphism. So, let us check that. So, what is the meaning of iota being Lie algebra homomorphism? Let us take iota of bracket xy for xy inside G. So, then we want to prove that this is same as bracket iota of x comma iota of y. Since the bracket xy where it will be mapped, okay, let us look at the bracket xy. So, using the inclusion, the bracket xy will go to the bracket xy. Okay. So, the bracket xy mapped via I just to the bracket xy, and then if you just take this pi, then you can see that pi is actually algebra homomorphism. So, pi of the bracket xy, so this is going to be exactly the bracket pi of x pi of y. Okay. So, now what is the bracket pi of x pi of y? So, that is same as, okay, so you can take because the pi is nothing but algebra homomorphism. So, you can see that this is pi of x pi of y minus pi of y pi of x. Okay. But that is exactly that iota of x bracket, okay, the bracket iota of x iota of y. So, this is indeed Lie algebra homomorphism. So, now if you actually think about it, given this theta, so we can actually prove that there exists unique extension theta tilde such that this diagram commutes, where theta tilde is indeed C algebra map. Okay. So, let me just write it here. So, given theta, which is from G to the bracket A, Lie algebra homomorphism, there exist theta tilde from UG to A, which is C algebra homomorphism, such that this diagram commutes. So, that can be written as, so you take iota theta tilde, the composition that should be equal to theta. So, this is what you get. Okay. So, let us see how one can prove this. So, this is just follows from the definition. Okay. So, given a map from G to the bracket A theta, note that it is a linear map. So, you have this natural inclusion from G to Tg. So, that means you have this natural extension, there exists theta tilde such that this actually commutes. Now, Tg to Ug, you have this quotient map pi. So, now we want to see that once you prove that this theta tilde factors through pi, then you are done. Okay. That means you want to actually say that there exists actually again theta tilde, same notation one can use such that this diagram commutes. Maybe we will use different notation, theta dash such that this diagram commutes, and this is immediate from the universal property of Tg. Now, we want to check we have this theta tilde such that this diagram commutes. So, now using now chasing the diagram, you can see that the bigger diagram will commute. Okay. But how theta tilde exists? To prove that theta tilde exists, all we need to say that if I take the kernel pi, okay, so that actually should contain this two-sided ideal I star. Okay. So, that is what we need to verify. So, sorry, not the kernel pi, the kernel pi is the I star. We want to say that theta tilde actually factors through this pi, okay, theta tilde factors through pi. So, that is what we need to verify. Okay. So, if we actually think about it, so what we need to verify. Okay. So, let us look at, so it will just boil down to, okay. So, if I take this theta dash of x tensor y minus y tensor x, let us take the bracket x y. Okay, let us compute what it is. So, this is going to be exactly theta of x, theta of y, because theta dash is the extension of theta, then minus theta of y, theta of x minus theta of bracket x y. But since theta is Lie algebra homomorphism, so this is going to be 0, as theta is a Lie algebra homomorphism. Okay. So, that means one can actually see that the kernel of theta dash, okay, the kernel of theta dash contains I star. So, then we can see that this map theta dash actually not the theta tilde, theta dash indeed factors through. Okay. So, that means we have this induced map theta tilde . So, now we can define this theta tilde from UG to A as you can take x plus I star and then send it to theta dash of x plus I star. Okay. So, now this diagram commutes and already this diagram commutes. So, entire diagram commutes. So, that proves the existence of theta tilde. So, now the uniqueness just follows from the fact that the image of G under this iota is generating UG. Okay. The iota of G generates UG, that is because I of G generates. Okay. The copy of G inside TG generates TG and pi is being surjective map. So, the iota of G generates UG. So, that tells you that theta tilde must be unique, because theta tilde is determined by theta. Okay. If you have two maps whose restriction is theta, then obviously because I of G generates them, so they must agree on all the elements of UG. That maybe you can just check it directly. So, this proves that indeed this given theta, you always have this extension theta tilde from UGT. So, now let us use this to prove that the representations of G corresponds to representations of UG. Okay. So, representations of G corresponds to representations of UG. So, what is the meaning of representation to begin with? To begin with, representation means it is a map from G to GL of V. Okay. So, now given this map theta, which is a Lie algebra homomorphism, Lie algebra map, you can easily see that you have this iota which is from UG, and then you can actually have this given theta, there exists unique theta tilde such that this diagram commutes. So, you can take theta and then send it to theta tilde, because theta tilde is a C algebra map from UG to GL of V. So, that means it is a representation of UG. Okay. So, it is a C algebra map, that means it is a representation of UG. So, this is the association that we can do. So, you start with theta and then send it to theta tilde. Now, if you take theta tilde, which is a map from UG to let us say GL of V, which is same as endomorphism of V. Okay. So, then how do you define theta? So, there is this natural map from G to UG, which is the iota. So, you just compose this map, then you will get map from G to GL of V. Since iota is a Lie algebra homomorphism, theta tilde is C algebra homomorphism, the composition will become Lie algebra homomorphism. So, that defines a representation. So, from theta tilde, you can actually send basically theta tilde composition iota. So, that is the map that you are actually defining from G to GL of V. So, this way you establish actually one-to-one correspondence between representations of G to representations of UG. Now, I will leave it as exercise to think about it, what irreducible, reducible, indecomposable representations corresponds. Okay. And it is easy to see that what they correspond in the category of representations of UG. Okay, I will stop here. We will continue with the property of the universal Naipian algebra in the next class. Thank you.